Okay, so we're looking at this problem, and the first thing you should realize is we just don't have a rule that can handle this problem. It's not power rule. Power rule would be like variable raised to a constant, right? It's not exponential rule. Exponential rule would be a constant raised to a variable. Right? Here you got a variable raised to a variable. So the only way to work around it is to find a way to bring it down. So that's why we use log differentiation to force that exponent to come down so that we actually have something to do. So yeah, natural log of both sides comes down. Okay, so now that this 2x is free to move, right?
Wait, that's 2x. Is it 2x or 2?
Sorry. 2 to the x.
Okay.
My bad. 2 to the x. This is okay. So that 2 to the x is free to move now that it's inside a log expression. So now we have rules that can handle this and this, right? Left side, we find a derivative. This is 1 over y dy dx, right? Natural log rule. Implicit as well. So we have 1 over y dy dx. And the right side, you guys recognize this as product rule, right? Yeah. F prime g plus f g prime. So there's my f. There's my g. Okay, so as a reminder, 2 to the x is basically, it's not base e, right? This is base 2. So the rule is for a to the u, right? A to the u, it feels like e to the u, right? It's the original function times exponent's derivative, but there's a little bit extra in front because it's not base e, so there's a little bit of conversion that has to happen. So there's a natural log of a, and then the original function, and then the exponent's derivative. Okay, so f prime. Sorry, I need to double check. Okay. What's f prime going to be?
2 to the x
times 1, yeah. Okay, you guys okay here? Derivative? Okay. G function, no changes. Back to f, no changes. And then g prime, okay? What's natural log of 3 minus 5x going to turn into? Yeah, we know the derivative of natural log of u is just u prime over u. Yeah. Okay, so you're basically at the derivative. Log differentiation just looks really messy, but we're basically there. Okay, we're basically at our answer. We just have to isolate dy dx. So I'm going to multiply by the reciprocal to move that y over to the right side. And in this, just try to merge as much as you can. I'm not going to ask you to do too much there. Oh, I can't merge them. I can just put them next to each other. I can't multiply the 2 and 5. Let me just say 2 to the x times negative 5. Okay, so that messes our answer, but there's one more thing we can do. We want to represent our answer, our derivative, just in terms of x. So what's one final substitution we can make?
The y function.
Yeah, let's bring that y, replace that y in terms of the original function. sorry, original function here. 3 minus 5x, that's raised to the 2x, yeah. Yeah, so if you know your first step and you know that you got to do product rule, it shouldn't be difficult. Your answer looks messy, but the process is not too bad, I don't think. But the important thing is recognizing the need for log differentiation. Right? I think that's the hard part. Mm-hmm. Oh, why is it a to the u, not e to the u? The reason why is because this is 2 to the x. Now, if it was e to the x, we would use the e rule. But this is 2 to the x. 2 to the x is base other than e. We use a to the u for bases other than e. So if it was 2 to the x, 5 to the x, 8 to the x, all of them we use a to the u rule. Yeah, it will have to be given to you. Like, let's say the problem was e to the x times natural log of 4 minus 3x. Then you would use e to the u rule, right? So if you see it, then you use it. But other than that, you want to use a to the u, right? These are both exponential functions, but we use different rules for these. Say it again. Oh, sorry.
Or can you just like give us another problem similar to that?
To this one here?
Yeah.
Okay. Yeah.
Does that make sense?
Okay, I have one here. Try this one. You guys, you okay? All right, let me. You may need to rewrite this first before you jump in too far.
Can that turn into x over 7?
That's right. Good.
X over 7?
So technically, it's parentheses raised to the x times, or raised to the 1/7, and the 1/7 times x, we can just merge it to be just x over 7.
Oh, okay.
All right. But yeah, technically you are raising both to its own exponent, but you can merge them together. So now we should recognize that as log differentiation, right? It's not power rule, it's not exponential rule. We got to use logs to help us put it into a different form.
So if it's in that format, it's going to be differentiation every single time?
It's going to be log differentiation every single time, that's right.
Okay.
Sorry to interrupt, kids. These are the two for tomorrow. I should be in by 4 period, but if I'm not, can they start again? Sure. Thank you.
If you want to write it as 1/7 x, maybe that's more manageable because then it feels like a power rule.
You can just change the x to a 1. Oh, 1 over 7.
Yeah, you can push that 7 out as 1/7.
Yeah, I didn't see the x out there.
It just feels a little bit easier that way. Okay, log differentiation. Okay, how to know when to add the ln? We add natural log when we're looking at a problem and we realize that there's no rules that match this problem. Right? This is not power rule. This is not exponential rule. This is a variable raised to a variable. Because we don't have a rule for a variable raised to a variable, we force natural log into it so that we can use the property to get that exponent to come down. Yeah, we only do log differentiation if we realize that there is no derivative rule that can handle that derivative, which is a variable raised to a variable. Right.
Are you supposed to move the 1/7?
Yep, let's move it down.
Oh, okay.
And now,
I forgot to move it out.
yeah, natural log first, and then move that down, and product rule should show up for you. Okay. Once we bring that exponent down in front, recognize the need for product rule. We have two expressions that are outside of each other. They're being multiplied. F prime G plus F G prime. Power rule for F prime, and then U prime over U for G prime. Natural log of Y, we got to have do implicit on the left side, 1 over Y dy dx. Push the Y over to the right side, and then finally replace the Y back in terms of your original problem. Okay, G prime, I did U prime over U. So U prime, the derivative of x squared minus natural log of x is 2x minus 1 over x. So U prime is going to be stuck here all over my U value. So I'll point to that. You got U prime over U. Okay, does that make sense?
Wait, why do you not do like, you know, at the bottom, 7, that part? Why do you not do the derivative of the other LNX?
Oh,
Is it,
the derivative of this LNX?
yeah, on the very bottom.
Oh.
I thought it would be x squared minus 1 over x. Or, I mean, 2x minus. Wait. Sorry, never mind.
What I did was I just tried to merge things a little bit more. So I multiplied the x through the numerator, and I just made it x squared minus 1.
Just how you combined 1 over 7x with 2x minus.
Right. I guess you may not have to clean up all the way that far, but yeah, I can show you. I made this really, I went back to x over 7. So I made this x over 7 times 2x minus 1 over x. And I distribute the x through the top and then the 7 through the bottom.
Oh, and you just can't combine the 7 on the bottom, so you just leave it.
Yeah. Well, I mean, I could have distributed through. There's a variety of different ways to display your answer. I just tried to get it as clean as I thought I could.
Could you put all of first, like, that one next?
Oh,
No,
this one here?
Yeah, like, no, can you put all of that on top of the 7 on that side of it?
No, unless we find common denominators.
No, not
Oh.
between the two things, just like put that and then add it. Like, no matter, like, could you put these? Could you?
Yeah.
Oh, okay.
You do that. Yeah. Okay, you can see.
You multiply y on both sides on the second to last step.
Yes, I did. I multiply y on both sides to get that y to shift over to the right. Then I replace the y back in terms of the original equation. Okay, we started with a function. We should be able to represent our derivative in terms of x. We shouldn't have to have y's in our final answer.
Oh, wait, so. Oh, you just put it back. Okay.
Yeah, I just put it back.
How? Where? What?
Okay, what's the issue?
I don't. Where are you getting the denominator of the second?
This part here?
Yes. Because for me, I just.
It's all kind of carried down from here, right? I just merged this together. I just merged those together and I got that. And I just kept bringing that down.
Oh, you replaced the y with the square root then?
Yeah, the y with
Oh,
the
okay.
square root. Were you guys able to get this stuff?
I got
Yeah.
the top part. I don't get how you get the x squared minus
Oh,
7x.
I did
Yeah,
not.
like it all
get
makes
that.
sense how you simplify it, but I don't feel
See,
like.
I
Oh,
have
I
the,
didn't
I
put it
have
over
the
you,
numerator of
that's
that, but I
what-
don't have.
It's because
like
you put it
a-
over you, that's what I need to.
That's fine. I think this is fine. You don't have to clean up past this. I just found ways to make it look a
Wait,
little
wait,
cleaner.
wait.
So you could write 1/7x.
You have to like,
Yeah.
see how I put u's like u prime, like 2x minus 1x. And then you put it over the original, I didn't do that.
Oh, okay, so here, we
Oh,
gotta do
okay,
u prime
I-
over u for this.
For that
Yeah,
whole thing,
I think I just did U prime and then just.
Oh,
Wait,
yeah.
so like, how
We
would you
need
do
this.
this?
Continue.
You have to do the inside of it, and then, see like, from the first log, and then, oh, that makes sense.
Yeah, so this is,
Yeah, that makes
I need to find the derivative for natural log of u, which is u prime over u. U prime is the
Yeah,
derivative of this.
Okay,
I didn't know you included like all this stuff. in
Yeah,
it.
that was a
Yeah.
moment.
Got it.
Just never give us derivative rules.
Now I understand.
Is this close to like the difficulty?
Yeah, you'd be able to do a lot differentiation problem like
This
this.
is feeling a lot like.
Are we gonna get like a list of everything that's gonna be on the test on Friday?
There is a list, yeah.
Yeah, I will, yeah, it should be there, but I will, here, you can take a picture of this. That should be on our website. Okay, let's look at. Let's look at a log problem. That may require some expansion before derivative. So anytime I see a log problem, I'm just trying to think of ways to take advantage of log properties. The purpose of log properties is so that we're not stuck having to do a messy derivative rule, right? So make life easier for our derivative step if we can spread all these into separate problems. I know it's log base 5, it looks complicated, but pretend like it's natural log and go as far as you can. And then at the end, we can adjust for the fact that it's base 5 and not base E. Okay, so what can we do first here?
You do minus log 5, 4 minus log 5.
So think of these as three terms here. Okay, so let me give you a example here. If I have natural log of A over BC, how would you expand that? So here's how we want to do it so that we don't have to do as many it is plus C, but then you got to worry about distributing. So my general rule is whatever lands in the numerator is part of a positive natural log or part of a positive log. Whatever lands in the denominator is part of a negative log. Okay. So do you see how this kind of matches with what we have here? Okay, so how would you rewrite this? Y equals log base 5 of 4 minus, okay, minus, yep, these are two separate things. Log base 5 of square root of 1 minus x. Okay, already our problem is beginning. Yeah.
Did you replace? Oh, you just pretended it was natural log and put log based on.
Right. So we're comfortable with natural log, but logs and natural log, they all share the same property. So I wanted to kind of start with something that feels recognizable, and then we adapt it to the problem in front of us. Okay, so already it's beginning to look a little easier because we are separating our messy problem into 3 smaller problems. But we can keep going. We can keep making these problems look even easier. What else can we do before we jump in? Say it again?
Bring the exponents.
Okay, bring the exponent down. Make this 1/2, right? Raise the 1/2 and bring the 1/2 down. Okay. Okay, so as a reminder, log base 5 of 1 minus x, the same thing as 1 minus x to the 1/2, which we can bring that exponent down. So all these log terms has a rule that we can use. The derivative of log base a of u looks a lot like natural log. It's just a little bit in front of that u prime over u. What do you mean? Oh, you mean power rule?
Yeah.
So power rule is derivative. This is log properties. Log property, you just bring the exponent down freely without changing the overall value. You just bring it down to make it easier for your next step. But there's no calculus involved. Right, and you only do power rule if it fits power rule, right? It needs to be a variable raised to an exponent before we can do power rule, right? We don't do power rule for something that is in this form. I know we have that exponent brought down, but it's a different thing, right? That's a power property. This is a derivative power rule. Okay, so all this time we haven't done any calculus yet. We've just gotten our messy problem into easier parts. Okay, so now we can do our derivative for each term, right? Y prime equals, okay, 1 over ln of a, 1 over ln of 5, times u prime over u. Let's force derivative, yeah. 0 over 4, so that's just going to wipe out, right? That's just going to be 0. Minus
2 over 5.
Mm-hmm.
Times 1 over x.
Times 1 over x. Yep. Coefficient stays. 1 over ln of 5. U prime over u.
Are you supposed to put the coefficient like in front of it?
It's up to you. I'm eventually going to kind of push it together and make it to, like you said, 2 over ln 5. Right now I'm just keeping everything separate, but all right, minus 1/2 times 1 over ln of 5. What's next?
Negative 1 minus x.
Mm-hmm. Okay, so this first term is gone, right? Okay. I'm just trying to clean up as much as I can. Yeah, this is not log differentiation, so we don't need natural log on the left side. So we don't have to do dy dx or 1 over y. right? We only have 1 over y dy dx if we're forcing natural logs onto both sides of the equation. This equation already has logs, so we just jump directly into its properties.
Why is it 2 positive?
No, that's not much true, because the last one was
Oh, sorry, that should be a negative. Thanks.
Oh, that's just one of the.
Like
Which
when
is
you
a
first start
natural
out.
log rolling.
Is it helps solve?
Log property.
Property or what it is.
I have a natural log of a to the n. I can write this as I have natural log of ab. I can expand this into if I have natural log of a over b.
It's not derivative.
Yeah, this is just so that our derivative is easier if we can get this to be cleaned up. And that applies for logs of other bases as well. It's just natural log is the one that we started learning on. Okay, do you guys want to do a one of each? I have a derivative of inverse at a point. I'll do that.
Is that the thing like the box?
The box.
Oh, yeah, I don't, that's just the
Okay, let's do that.
box.
Okay, I can run through the steps here. The big idea here is that a function and its inverse are going to be sharing kind of flipped order pairs, right? Any order pair for a function is always going to be flipped on the inverse side of things. But then at those particular points, they're also going to share a relationship in their slopes, right? They're going to be reciprocals of each other, okay? So the first thing you have to realize is that if you're asked to find the derivative of inverse at a point, understand that this is the x value of the inverse, but it's really the what? But it's the what of the original function. It's the y value. So just have to understand that whatever they give you, just know it's really the y value. Okay. So I like to use this chart to kind of help map my progress here. Anything I put down here is slope related. Anything I put up here is order pair related. You don't have to use this chart. It just kind of helps me organize my information. I know that my order pair on the inverse side of things is going to be 2 something. But I already know that since I'm using the original function to help me work through this process, I know this 2 is really the y value. So, okay, so this is where our steps come in. Okay, the x value they give us is really the y value of the original function, and from here, I can kind of figure out what the x value that will allow me to get to my slope, and then once I get to my slope, I can circle back and figure out the slope of the inverse. So just understand whatever they give you, just stick it in the y slot of the original function. Okay, good so far. Now, a lot of times these are not going to be solvable by hand. So we're going to just try to do guess and check. I'll bring everything over to one side. I'll subtract 2. X cubed plus 2x minus 3. Okay. We don't have a calculator. It's not factorable. We're going to go through guess and check. But it should be an easy number to find, meaning that you just start with 0. If 0 doesn't work, then try 1. If 1 doesn't work, then try -1. Do it a couple of times and you'll get it. Find an easy number like between -3 and 3. So let's see what numbers can work. If I plug in 0 for x, is that going to make this a true statement? 0 plus 0 minus 3 is not equal to 0, right? Okay, so it doesn't work. Okay, how about 1? Yeah, 1 cubed is 1. 2 times 1 is 2. 1 plus 2 is 3. 3 minus 3 is 0. Okay, we have the value that connects between these two, between the x and the y value. So I'm just going to fill this in. I know that, okay, my function and inverse function are going to be one function is going to have order pair 1, 2. The inverse function is going to have order pair 2, 1. Okay. So because we're only able to work on the function side of things, we're going to find the slope of the f graph at 1. Whatever the slope of the f graph at 1 is, that's going to lead us directly to what we want, which is the slope of the inverse at its corresponding point. So how can I find f prime of 1? Yeah, find a derivative and then plug in 1, right? So 2 steps here. F prime power rule, what do we get? From here we can find the slope. F prime of 1 is 5. So the inverse at 1, 2 must be 1/5. Okay, let me draw a picture to kind of help convince you that what we've achieved here. No. I just want to show you so that these numbers make sense in your head. So I want to kind of demonstrate to you what these numbers mean from a graphical perspective, right? So you have a function that has order pair 1, 2. So imagine this, right? Order pair 1, 2. These are inverse functions because you can fold the graph over the diagonal line and make them overlap. So you got 1, 2, you have 2, 1 over here. So there's a special relationship in terms of their slope. One slope is going to be, let's say this is 5, which is very steep slope. And this slope is going to be much more gradual. And that's going to be a slope of 1/5. So that's what we're establishing through going through this. Trying to use the function to kind of help using this relationship. If I can find out the slope, I can turn around and know what the slope is at their corresponding points, right? If 1, 2 lives on the function, I know 2, 1 lives on the inverse. So that's what we're doing with this whole chart thing. But to recap the steps, whatever they give you, stick it into the y slots, figure out what the x is. Once you figure out the x, find the derivative, find the slope, get that number, and then flip that number. Okay? All right, let's do an implicit problem. All right, copy this down. Okay, can you spell out for me what is involved here for our derivative process? Or what do you see? Got you good?
Yeah.
Okay, so implicit because you have y's mixed in the equation, that's good. Product rule because you have x, y. Anything else? Yeah, that's what I would do. If you don't expand, you can still do it. It's just a messy u value, right? Let's make life easier on ourselves. Let's expand this first. Then our derivative will be a lot easier. Okay. So here's my next step. Okay. Split up natural log of xy into natural log of x plus natural log of y. And now I'm ready for the derivative, right? I can do u prime over u for the first two terms. The xy will be product rule. And careful with that 50. What happens to that 50? 0. Good. Yep. Natural log is 1 over x. It's good. Natural log of y is 1 over y, but anything dy over dx, right? Anytime you're involving y's derivative, you got to include that dy dx. Okay, so once you can reach that step, everything should feel easier because you're done with the calculus. You're just trying to rearrange, group dy dx together so that you can factor it out, so you can just solve for dy dx. Okay. F prime g plus f g prime, x becomes 1. We keep the y back to x, and then y's derivative is 1 dy dx. Okay, are you good up to this point? Okay, I'm going to group the dy dx terms together. Put those on the left side. Move the 1 over x and the y over to the right side. And then factor out the dy dx. Sorry, I'm not going to ask you to clean up all the way. If you leave it in this form, that's fine. But what I did was try to find common denominators to make it even cleaner, but this is fine.
So the thing you boxed for is.
Yeah, this is the yeah, that's fine. Yeah. Let's see, is there one more to do?
How do you divide it? 1 over y plus x.
Okay, how about a tangent line equation problem? Okay, last one here. f of x equals e to the negative x, natural log of x at 1, 0. Reminders, derivative for e to the u and natural log of u are needed. Okay, what do we need to apply for the derivative? Okay, what else? And what else? I mean, can we just use those two derivatives and stack them on top of each other? Product rule. Product rule. Or you can bring that e to the x down and go through quotient rule, but I just left it up to the top and do product rule. Now, if it was e.
Product rule first?
Yeah.
Oh.
Yeah. Now, if it was e to the negative x plus natural log of x, then we can take the derivative of them separately and there's no problem. But the fact that they're being multiplied, we got to do product rule.
Okay.
Once you find the derivative, then you can clean up a little bit, or I guess the derivative is not that important in terms of this form. We just want to find the slope. So if you're ready to plug in, you can. I just decided to clean it up a little bit more before I plugged in 1 to get the slope. Okay, you guys okay with product rule there?
For the derivative of g, I thought you have to put like that's the derivative of L next. Don't you have to put L next below that? Like, so
Well, if you look at the derivative for natural log of u, it's u prime over u, right? Or u is x, so x derivative is 1, and the u is x, so it's 1 over x.
Where you getting? You said about the derivative. Because it's one, the derivative of x is just one.
yeah, I get that. So you have the derivative on top, and then you have the regular L next on the bottom.
No, but the L and N goes away.
Yeah, if you look at the rule, right, natural log of u doesn't have any natural log in it. Okay, so you're thinking the u value as the whole natural log. The u value is just what's inside the natural log.
Okay. Yeah.
Okay, once you find the derivative, you guys okay up to f prime? You can replace all the x's with 1 and see what you get for your slope.
So keep it 1, 0. First one.
Let's see.
Oh, it's just e to the 0 is 1.
Yeah, e to the 0 is 1.
Just
Maybe the one is just you.
eat the zeros. Just tell it.
Okay, where are you guys stuck?
How, what is negative ln times 1?
Oh, it's negative natural log of 1. So natural log of 1 is just 0.
Oh, okay.
Yeah, natural log of 1 is 0. Right, we like to keep
You
coming.
find the slope. And then,
Yeah, we find the slope by entering the 1 into the derivative function. And then once you get that slope value, we can dump it back into point slope form.
That's the one of 1 0.
that's 1 minus.
Yeah.
Yeah, the graph.
No, because like,
Natural log of 1 is 0, natural log of e is 1. Yeah, so memorize this graph. It's going to be really helpful.
What's natural log over e?
Natural log of e. I don't know if we have that. Oh, it's natural log of 1 over e, so 0 over e, which is 0.
Just memorizing that graph.
Hmm?
So why is that graph important?
This is going to be helpful for curve sketching as well, in order to approximate like natural log of 1/2, natural log of negative 1/2,
So
natural log
just
of
a
2.
natural log.
Yeah, this is a natural log graph, which doesn't look like much, but it provides a lot of information. Okay. All right. Help session tomorrow morning and Friday morning. All right.
Is that like one of every problem except for like the
Except for the curve sketching and the particle motion.
yeah, I get the part.
Okay.
yeah, both of that ones.
Yeah.
The only
It just
thing
feels
I
like the
do.
same stuff.
That was hard. Oh my God.